pH can be a fairly difficult topic for students to wrap their heads around, and the calculations of pH are a little difficult, but they're really not terribly difficult so long as you understand that calculating a pH is a process that proceeds through a stepwise manner. And so this little mini lecture is going to be looking at a couple of pH challenges, varying degrees of difficulty, and showing you the process by which you calculate pH and hopefully provide you with a strategy for tackling pH problems. So let's look at a standard pH challenge. This is a very typical type of pH question. Calculate the pH of a 2-liter solution containing 10 milliliters of 5 molar acetic acid and 10 milliliters of 1 molar sodium acetate. If you want to try this challenge on your own before we do the walkthrough, go ahead and pause the video now and see what you come up with. I highly recommend that you do this because when I go through the walkthrough, you'll be able to reverse engineer the solution and you should be able to pick out if you're doing everything correctly or if you're having some problems in anywhere in the basic solution of the problem. One thing to note is that we do have some mixed units. We have milliliters versus liters, so we want to be thoughtful of that, and our molarity is fine, it's just molar and molar. So go ahead and pause the video now if you want to try this problem on your own. Okay, so assuming you're ready to go forward with the walkthrough, let's take a look. So a standard pH challenge, here's our walkthrough. Our first step is to identify the type of question. This is true for every question, not just pH questions. So looking at this question, this is a pH question. We will know when we're doing pH, what we really need is ultimately the ratio between the acid and its conjugate base. There's no neutralization in this question. If we go back and look at the details of the question, we see that it's just we have some acid, we have some base, what's the pH? We're not neutralizing anything by adding additional acid or base after the solution is made. So now we have to identify what is given. If we look at the question, we have the total volume of the solution, and we have the partial volumes and molarity of the acid, weak acid, and conjugate base, and we can be given the pKa. So now we need to determine what needs to be solved. Well, we need the final concentration of A minus, or the conjugate base, and the final concentration of the acid, HA, and from those two we will be able to determine the pH. So how do we do all this? Well, step 1, we need to determine the concentrations of A minus and HA. Now A minus is the conjugate base, or the acetate, and the or sodium acetate, and the HA would be the acetic acid. So the key to finding a conjugate base is something that ends in ATE. Very frequently, if you had acetic acid, that would be deprotonated to acetate, and that's what we see here. We have the partial molarities are necessary, but the molarities given are not the final molarities. They are the molarities of the materials when they were added to the solution, but not the molarities of the materials once they are in the solution. And so to solve this problem, we need our classic M1V1 equals M2V2. And this is a great little equation. It's all about figuring out a dilution, and it is absolutely perfect for that. So in this case, we have molarity 1, volume 1 of a substance, and then that will give us molarity 2 or volume 2 of that substance in a different solution. So for example, if we go with what was given, we have a 1 molar of a 10 milliliter, but notice I've converted it to liters, 10 milliliter acetate, the conjugate base. So that's M1 is 1 molar. V1 is 0.01 liters, because remember I went from milliliters to liters. And then M2 is the final solution, 2 liters, and the sodium acetate's concentration is what we're trying to find out. And you might say, well, wait a minute, why are you using 2 liters instead of, why aren't you adding the milliliters to the liters to get the final volume? Well, because the milliliters it's 10 milliliters out of 2 liters. There isn't enough volume change here for us to worry about that. Now that's kind of a subjective call. You could certainly increase the final volume by the volumes of both materials. You could do that. But again, these individual few milliliters are not changing anything. So if we solve for x milliliters, we divide both sides by 2 liters, and that eliminates our liters, and we are left with xm equals 0.005 molar. So molar equals molar. So our units cancel appropriately, and we have 0.005 molar. Our acid works similarly. We'd set it up the same way. 5 molar acetic acid. We convert our milliliters to liters, and we are looking for the final molarity, and we know the solution is 2 liters, and we get 0.025 molar if we solve for this molarity. Again, the liters cancel, the moles do not, so we have molar equals molar. So our units line up, and that's very, very important. Now that we have our conjugate base and our acid, our A minus and our HA, we simply apply the Henderson-Hasselbalch equation. So pH equals pKa plus log A minus over HA. Now that pKa is the pKa of acetic acid that we're using specifically. An important thing to remember about pKa is it tells you the pH at which this ratio would be 1/1, where the concentrations of the conjugate base and the acid would be identical. They're not in this case, but if we add everything in, 4.76, which is the pKa of acetic acid, plus the log of 0.005 divided by 0.025, and you get a final pH of 4.06. A very standard pH challenge of just calculating the pH of a simple solution. But sometimes we need to do something a little bit more complicated. Now, while we're still not to the hardest types of challenges here, this is definitely more difficult. So let's look at the question. Calculate the pH of a 1 liter solution containing 0.1 molar formic acid and 0.1 molar sodium formate before and after the addition of 1.00 milliliter of 5 molar sodium hydroxide. How much would the pH change if the sodium hydroxide were added to 1 liter of pure water? So we have a whole lot happening in this question. We need to find out several things. We need to find out the pH of the solution before the addition of the strong base. Our sodium hydroxide is a strong base. We need to find out the pH of the solution after the addition of the strong base, and we need to determine the pH of the same amount of strong base added to 1 liter of pure water. A couple of things to note is we do have a unit change. We have milliliters to liters. Our molarity is fine. If you'd like to solve this problem yourself, go ahead and pause the video now and give it a try. I recommend that you do so. Okay, assuming you're ready for the walkthrough, let's take a look a little bit about this challenge. So as always, we're going to identify the type of question. It's a pH question, which means we need the ratio of conjugate base and acid, and there is neutralization in this case because we're going to have a solution that contains some amount of conjugate base and that's cognate acid, and then we're going to add a strong base to it. Now we could also add a strong acid, but this question is challenging us with a strong base. Identify what is given. Well, we have the total volume of the solution, we have the concentration of weak acid and conjugate base in solution. So we don't have to solve that this time. Notice it wasn't some amount in so many milliliters that are then in 2 liters or whatever. This is the molarity of the material in solution. So we actually have our job simplified a little bit here. But what we don't have is the volume and concentration of the strong, or the final molarity of the strong base. We are given the volume and concentration. So we're going to have to solve that. And the pKa would be given for formic acid. Remember, the cognate conjugate base of formic acid is going to be formate. So what needs to be solved? Well, as mentioned already, there are basically 3 things we need to solve. pH before and after addition of the strong base, and pH of the same amount of base added to pure water. Okay, so what is it we need to do? Well, we know we have our 3 problems, so we're going to have to work on each problem individually. pH before the strong base. This is given in the question. This is one of those moments you can look at a question and go, oh, thank goodness I understand concepts in biochemistry. Because if you look at the question, the concentration of the conjugate base and the concentration of the acid were the same. Go back and look at the question. They were absolutely the same. So what we know conceptually is the pKa value of an acid is the pH when half of the members of the species are deprotonated and half are protonated. So in other words, when the concentrations are equal, the pH must equal the pKa, which is 3.75. So we know, without doing any calculation at all, that the pH is 3.75. Now for practice, if you'd like, go ahead and apply the Henderson-Hasselbalch equation, but what you're going to see is the log term falls out of the calculation. Question 1 is finished. Question 2, however, we're going to have to do some work, and this is a neutralization question. So we already know the molarities of the conjugate base and the weak acid, and that is going to change upon the addition of the strong base. So we just need to figure out how much strong base we have in terms of molarity. So we're going to do this now. We're going to figure this one out. So we first figure out the molarity of the strong base, and we go back to good old M1V1 equals M2V2. So we know we have 1 milliliter, 0.001 liters of 5 moles or 5 molar strong base. And we want to know what that value is going to be molarity-wise in the 1 liter solution. Again, the 1 milliliter and the 1 liter are not really interacting. We don't have to worry about that 1 milliliter, and so instead we get our final 0.005 molar strong base. And one thing to remember about strong bases is it's 100% disassociation. There's no pKa's or anything to worry about. It completely disassociates, so we can assume all of the hydroxide, in this case from the strong base, is made available to neutralize in our weak acid conjugate base solution. So we're going to use all of this 0.005 molar. So now we do the neutralization. Well, we have to understand conceptually what's going on. By adding a base, we are eliminating acid. Okay? The hydroxides are going to pull the protons off of our weak acid, and by doing that, the weak acid is converted to the conjugate base. That's essentially all that goes on. We take our acid, we remove the proton, and you have the conjugate base. So since we know all of the proton from the sodium hydroxide is available, we simply need to decrease the amount of acid. Our molarity is given, and we're going to convert that amount to base. So we take our 0.1 molar weak acid, we use up all of the base, deprotonating it, we get 0.095 molar weak acid remaining. Then we're going to, this is important, we're going to increase the amount of conjugate base. So remember, whenever we deprotonate a weak acid, it becomes a conjugate base. So the same amount of weak acid that was lost, 0.005 molar, is now added to the base, the conjugate base. So 0.1 molar plus 0.005 molar gives us a final conjugate base concentration of 0.105. So now we have new ratios. They are no longer the same, so we know the pH has changed. For the pH to have not changed, the ratios could not change, but the ratio has changed, so we have a new pH. So we can simply apply this to the Henderson-Hasselbalch equation. We start with our pKa plus log of conjugate base, remember that's A minus, the deprotonated form, 0.105 over 0.095, and you get 3.79. What you want to notice here, because this is important conceptually, is we didn't move the pH that much. Okay, you went from 3.75 to 3.79. So this system really did resist the presence of the strong base. But you might say, well, wait a minute. Okay, but you already said there was 1 milliliter that doesn't have really any impact on 1 liter. It's 1/1000th of a liter, so why would we expect the pH to change? All right, so this is why we have the third part of the question, which is calculate the change from the same amount of strong base added to pure water. Okay, so our last question, what about the same amount of strong base in the same volume of pure water? Well, for this we need to work on a slightly different equation. We need to use the ionization of water. So the ionization equation for water is the concentration of proton times the concentration of hydroxide is equal to 1 times 10 to the minus 14. You should recognize that 14 as being on the pH scale. And so we'll simply rearrange this. The one thing we know, we can use the concentration of strong base we already calculated, and so we'll simply rearrange this. We'll take the concentration of proton is equal to 1.0 times 10 to the minus 14 divided by the concentration of hydroxide. And so that's this rearrangement here. And by doing this rearrangement, you get 2 times 10 to the minus 12 molar protons in the solution. So now that we know the proton concentration, we don't use Henderson-Hasselbalch, we use the standard pH equation, which is pH is equal to the negative log of the proton concentration. And so we take our negative log of 2 times 10 to the negative 12th molar, and pH is 11.7. So notice, just by adding 1 milliliter of sodium hydroxide, our pH jumped from 7 to almost 12. Okay, let's just consider it 12 just to keep the analysis easy. 7 to almost 12 is 5 pH units of change. Now remember, a change in 1 pH unit is an order of magnitude. That's times 10 because it's a logarithmic scale. Whereas if we had the buffering system, we went only from 3.75 to 3.79. And so that brings us to the takeaways for this analysis. The first is to really notice the strong base barely raised the pH of the buffered system, whereas that same amount of strong base, a very, very small amount of strong base, dramatically changed the pH of pure water. It really had no effect, almost no measurable effect on the buffered system. And why is this important? Because enzymes, as we know, are sensitive to pH changes due to pKa values of their amino acid side chains. So if you have things like lysine, which is a protonating deprotonating amino acid, or glutamate, which is also a protonating deprotonating amino acid on the side chain, they have pKa values, which means they do buffer. But if the systems themselves weren't buffered and the pH changed dramatically, we could move beyond the pKas of those amino acid side chains and really change their character to either carrying a charge or not carrying a charge, which would have deleterious effects on the enzyme. And so our final concept in all of this is living systems have extensive buffering to prevent pH changes due to standard metabolic systems and activities.